accept the recording, then we can start. So, once again, welcome to today's training for the Kenya Mathematical Olympiad. And the topic for discussion today will be trigonometry. Can you hear me?
Yes.
Yes.
Good.
Yeah.
So the topic of discussion today will be trigonometry, and I'm happy to see we have quite a number of participants. That's a very good number. Over 60 participants. It's a holiday, but we decided to just go on with a talk and just take maybe 1 hour of your time for today. Hopefully, we'll find it beneficial. So now I'll need you to confirm if you can see my slide.
Yes.
Yes.
Can see my slide. Okay. So my name is Dr. James Katende. I'm from the School of Mathematics, the University of Nairobi. In particular, the Department of Pure Mathematics, and I'm part of the team that organizes the Kenya Mathematical Olympiad. So if you can mute your microphones, please, so that we... Yes, thank you. So you mute your microphones, but if you have a question in between, you can always raise your hand. You don't have to wait until the end to ask the question. Or if you have a comment in between, please feel free to raise your hand, and I will give you an opportunity to participate. So you do not have to wait until the end. So we shall look at a very simple view of application of trigonometry. So I didn't have enough time to put in more detail, but this will give you a rough idea of what you can do with trigonometry before we start talking about it. So this topic of signal processing is a very applicable topic, and used in many applications like processing, even things like sound processing and so on. Things like oil exploration, as we shall see in a short while. So it's a very applicable. We will barely cover any substance of this, but you'll get a rough idea of what it is. So we start now. A signal is simply a description of how one parameter will vary with another parameter. So an example is voltage changing over time in an electrical circuit. For those who are doing physics or engineering, if you're in university and so on, you probably do this all the time. There are other signals as well. You can have signals like the stock prices changing over time. That is also a signal. Sometimes they have cycles and they can. You can also have, say, signals like the price of a commodity in the market changing over time. We'll be seeing a few more examples shortly. So one area where it can be applied is medicine. Now in medicine, the ECGs can be used to diagnose heart disorders. What happened is the ECG measures some signals that come from the heart, some vibrations, and is able to record them as this ECG. And it can pick up the different signals. I think they're usually about 5 different signals. And any one or some of them missing usually are an indication of a heart disorder. So that is one place where it can be used. So one thing you probably should note about this is that it doesn't look like the normal smooth trigonometric functions that you use, but we'll explain why in a short time. So another area where this is used is in hydrocarbon exploration. In oil and gas exploration, usually they can we please put off the microphone? Thank you. So when exploring for oil, instead of digging without any prior research, Benjamin, someone, please switch off your mic. Okay, I need to find Benjamin. There. Try to put your mics off so that we have a little less interference during the good. I think now we are clear. All the mics are off. So I'll just go back to the presentation. Oh, there's something I've lost again now. Yeah. Perfect. Good. So here we had oil and gas exploration. What happens with the oil and gas exploration? You have some track which hits the ground and throws some vibration into the ground. So what happens is, as it goes into the ground, there are some phones, they're called geophones, that are put along the line to pick up the signals as the waves are reflected back. So those signals are stored and they can be analyzed to be able to work out a profile of or cross-section of the section which is being explored. And they can analyze that to tell whether the prospects of finding oil are good or not good at all. And that saves them the trouble of having to drill fast. Another area is seismology. This is a signal from an earthquake. Also, all this can be analyzed using trigonometry or some parts of trigonometry. Now, you'll also notice again that this curve is not as smooth as the ones you would normally see in your trigonometry. And we are about to see the reason for that. So that will be the next step. So if you look at this slide, we have four different waves, and they all have different heights and different frequencies and so on. So on their own, they look very smooth and nice. So this is what you would learn in class. But in real life, what you get is, this is what you get now, this kind of signal. So what this signal is made up of is a number of these smooth signals. When you add them up, you end up getting this kind of rough signal. So although these ones are just a few, when we add them up, this is what we get. But you can see now it's getting closer and closer to something realistic. The other thing that you may have to add here is noise. I didn't add any noise. Noise is what adds this random variation in the wave. But now when you add these ones, this is what you get. So what signal processing does is, once where you start from is this point. You start from this wave and you don't know what these components are. So you have to find these components. You start with this wave, then you have to find these components that are in them. So once you work it out, you're able to recover these four components. But initially you didn't know they were there. But signal processing helps you to recover these four components. If you are studying financial data, this can be seasonal cycles. You know, there are different cycles. There's someone who's okay. Let me just take care of that first. There. So this signal processing helps you to split this signal back into its pieces. Now, if you go back a little, for the heartbeat, usually you have different signals in them. So each signal has a different frequency and lasts for a different times. So a doctor will be able to tell if one of them is missing. When they try to break it down, then they might be able to diagnose some disorders in the heart. So the techniques used for this are a bit beyond the scope of this class, but that was just to show you that these trigonometrical functions really have a lot of application. So you simply try to find the dominant cycles. By dominant cycles, I mean, if you look at this example, this last term, the amplitude for just this last term is 4. So it actually has a lot of power. So signal processing will be able to find this cycle, and it will also be able to tell you that it has more power than the others. You see the coefficient here is 4. So it's more than this one, which is 1. Then there's 0.5 here, and there is 2. So the next most powerful will be 2. And the signal processor will be able to pick out all that information. Like I said, again, the scope is a little beyond the class, and we will not go into the details. If you have any questions, please, you can raise them. So one of the techniques normally used for this is called the fast Fourier transform. It's a very versatile technique and works in so many applications. Maybe someday we shall cover it also. So now we move to measurement of angles. We look at two distinct ways of measuring angles. One way would be to divide the circle into 360 equal parts, which we call 360 degrees. The other one is to compute the radian. The radian is simply the angle subtended at the center by an arc of the same length as the radius. So if you find an arc length here that is the same length as the radius, the angle subtended right here at the center would be 1 radian. Now, because we know that the circumference of the circle is 2 pi r, it means the total angle at the center should be 2 pi r divided by r. So that will be equal to 2 pi radians. Radians are very useful to work with, especially when you're working with calculus. Later on, radians, you will have to work with radians. You can't work with degrees, but we shall work with degrees for most of this class. So how do we measure a positive angle? We measure a positive angle in the anti-clockwise direction. So if I'm measuring positive, it means I go in the anti-clockwise direction, and a negative angle means I will go in the clockwise direction. So it's sometimes useful to be able to convert from radians to degrees, and we use this relation where 2 pi radians will be equal to 360 degrees. So using that, we can see that 1 radian is approximately 57.3 degrees, and 1 degree is approximately 0.0175 radians. Sometimes this symbol C as a superscript here is used to represent radians, the small c at the top, or we just write it as, we just add this RAD to mean radians. So some of the common angles that we normally meet, like 180 degrees, we know that would be pi, 90 degrees will be pi over 2, 60 will be pi over 3, 45 will be pi over 4, and 30 will be pi over 6. So from the way the radian is defined, you can easily compute the length of an arc which subtends an angle theta radians at the center of the circle. That will simply be given by S is equal to R multiplied by theta. Right? Because 1 radian is is an arc length here of the same length as the radius. So if you have an angle here in theta radians, the number of arc lengths will be R multiplied by that angle. So it gives you R theta. In the same fashion, you can see that the area of the minor sector will be given by theta over 2 pi multiplied by pi r squared. And this is just the same as half r squared theta. So this only works if your angles are in radians. If they are not in radians, this will not work. These formulas are only when your angles are in radians. So you are familiar with these trigonometric ratios, and this is how you usually compute them. You start with a right angle triangle. and you work out the sine, the cosine, and the tangent. The sine is usually the opposite over the hypotenuse. The cosine is usually the adjacent over the hypotenuse. And the tangent is usually, hold on, I need to mute someone. Yeah. Okay, there's someone who has raised the hand. Swale Salim, you have a question?
Yes.
Okay, ask.
I've lost, I wanted to know the area of the minor sector. You just, yeah, that one.
Okay.
It is.
So remember that this only works if you measure your angles in radians. So that means you have to be careful. If you are working with a calculator, you need to set your angle to your calculator to radians to be able to work with this.
Okay. Okay. And what about the first one?
Which one? This one?
Yes, yes.
Both of them work only with radians.
Okay.
They follow directly from the definition of a radian. So the definition of a radian is what leads you to these two formulas.
Okay. Okay, thank you.
Okay. Because if you're working with degrees, then you'd have theta over 360. 360, yeah. But now we have 2 pi, which means you're working in radians. So the total angle at the center usually will be 2 pi, as we have seen. In degrees, it's 360. So these are the ratios you probably are familiar with. Now, it doesn't really matter the size of this triangle. You can also get another similar triangle, and it will still give you the same ratios. So what we want to do is to work with a triangle where the length of the hypotenuse is equal to 1. Violet Kerubo, you have a question? Someone raised a hand, but
yes.
Yes, you'd have to ask a little quickly so that we
I
one person. I can't hear you.
When you are the changing radians into this.
Okay, I don't know. Did anyone?
Never got you.
Did anyone get what she's asked? I can't get what she's asking.
I'm asking.
Yes.
I'm asking.
Is that the slide you are looking for? Do this. Type your question in the chat. I'll look at it later. We are not able to hear you clearly. There must be a problem with the connection.
Thanks.
Just type in the chat. I think for the chat, I can't respond immediately, but at the end, you can still ask. You can always come back to this slide. So, as I was saying, we want to pick a triangle where the hypotenuse has length 1, so that this length OB will be equal to 1. And when we do that, we can use the unit circle like this. So we restrict ourselves to the unit circle. And this is the unit circle. The unit circle is just a circle centered at 0 with radius 1. So if you want any angle, you can shift this radius all the way around and you get any angle from 0 to 360. But now since the hypotenuse is of length 1, the cosine will just be the projection. You see this radius, the cosine of this angle theta will just be the projection onto the x-axis. This length ON will be the cosine, and the length OM will be the sine. You can try to do that because if you get the sine of theta is supposed to be the opposite over the hypotenuse, but the hypotenuse is 1, so it's basically just the opposite over 1, which is PN and MO are the same length. The same for the cosine. So at this point, our definition of a sine will just be the projection of this line making the angle theta with the positive x-axis. So its projection onto the y-axis will simply be the sine of the angle, and its projection onto the x-axis will be the cosine of the angle. So with this one, you can observe the following, that the cosine of theta is the same as the cosine of minus theta. Let's just go back to the, so I didn't draw it here, but if you remember, if you're measuring positive angles, you measure clockwise. So this is theta measured clockwise. Negative theta would be the same, but going anti-clockwise, so that your line now would be going downwards towards this end, and maybe up to some point there on the circle. But since it's exactly the same angle, only in a different direction, the projection will be the same, be negative theta, but the projection will still be the same thing. So the cosine of theta and the cosine of the negative of theta will both be equal, right? So that covers this first property. The other one is that the sine of theta is the same as the negative of the sine of minus theta. So we can go back a step. So if you drop, use the same radius again, making an angle negative theta with the positive x-axis, what will happen now is that the projection will be, if you project it onto the y-axis, it will end up on the negative side. It will be exactly the same length as the sine of theta, but on the negative side. So the sine of minus theta is the same as the negative of the sine of theta. So this, for those who are familiar with functions, this means that the cosine of theta is an even function and the sine of theta is an odd function, but that's not important so much. We won't need that now, but it's useful information. So another thing you will notice when you apply if you compute the ratios in this form, you will see that since the length is 1 of the radius, this sine cannot exceed. It cannot be more than 1. It can also not go below negative 1. The same with the cosine. It cannot exceed 1, and it cannot go below negative 1. So that gives us the upper and lower bounds for the sine and the cosine function. So it means negative 1 will always be less than sine theta, and sine theta will be less than or equal to negative 1, and the same with negative 1 will be less than or equal to the cosine of theta, which is less than or equal to 1. Okay. So did I skip something here? I think so. Now we can, when we draw the graph of sine theta, this is what you get. Maybe I should have drawn a little more of it so that you can see how it works. But what happens is that it will start at 0 here, go all the way down, and come back up again at 360. So this pattern is repeated over and over again. So after every 360 degrees, or after every 2 pi radians, this wave is repeated. So that is what gives us these two properties. Just by looking at the wave, you'll be able to see that that is what happens. So to be able to see that why it repeats, we can just go back to this circle. So what happens is that you keep going around. If you start from here, for instance, and you're measuring the sine, eventually you will come back again to the same spot after one full cycle. Then you repeat the same cycle if you're still measuring larger and larger angles and so on. So again, you come back, it keeps repeating. That's why every 360 degrees, it goes around and comes back to where it started and keeps going round and round. So that's why it repeats. So a key thing to note is that the sine of 0 is actually 0. And it will be 0 again at 180 degrees and also at 360 degrees. Those are the points where it cuts the x-axis. And then this repeats every 360 degrees. Now, another thing you'll observe is that the sine of theta is the same as sine of 180 minus theta. You can, this is possible. If you put, suppose you get a graph here, you draw a line here, assume your angle theta is somewhere here. Since this curve is symmetric, you can draw another line from the x-axis going up with the same height as the one that will be drawn here, theta. Now the distance from that point all the way to 180 will be the same as, will be theta. So that the angle here will be 180 minus theta, and we'll have the same sign as an angle theta on this side. Unfortunately, I didn't draw the diagram for this, but I hope that explanation makes sense. So basically, you pick an angle somewhere here, theta, you drop a perpendicular all the way to the curve. So that same distance theta here, you come back on this end and move backwards that distance, and then you go all the way up a perpendicular again to the curve. So they will both be at the same height, those two lines. But this point here will be 180 minus theta, and the one on this side will be theta, and they will all be at the same level, and therefore they have the same value for the sine. So these properties are properties that you need to keep in mind because they come in handy as we go along. Now we look at the graph of cosine of theta. Again, it has the same properties as the sine. It repeats every 2 pi radians or 360 degrees, where n is an integer. And we also observe that the cosine of pi minus theta is the same as the negative of the cosine of theta. Again, these are important identities. So let me see if I can, should have drawn a diagram for this. But we'll try to do this here. Again, if you measure an angle theta on the x-axis, so that the angle, say, is somewhere here, and you drop perpendicular all the way to the curve, somewhere there. If you come to 180 is pi, right? In degrees, it is pi. Subtract that same angle here and drop it all the way. So those two lines will have the same height. The one on this side and the one on that side will have the same height. The only difference is that they will be of opposite sign. The one on this end is positive, and the one on this end is negative. So that the cosine of pi minus theta is the same as the negative of the cosine of theta. So then the other ratio that we have not defined, or rather have not defined using the unit circle, is this one, the tangent, and it's just simply the sine of theta divided by the cosine of theta. If you work it out as Pn over On, since Pn is the sine of theta and On is the cosine of theta, that's what we get as a sine. Remember, the tangent is obtained as the opposite of adjacent, right? So the tan of theta will be the opposite, which is Pn, divided by the adjacent, which is On. So now this function is defined for values of theta where cosine is not equal to 0. And you can see where the cosine is 0, we have asymptotes. So you see, like at negative 90, at 90, and so on. So there's a gap of 180 degrees between each cycle. And because of that, this function will repeat itself every 180 degrees or pi radians. So the cycle now is changed to 180 degrees for the tangent. So every 180 degrees, it will repeat. This. Just give me a minute. I need to mute the mic somewhere. Okay, so this is what the curve will look like. So also the tangent curve is not limited. It goes all the way to positive infinity, and again all the way back to negative infinity. And that keeps repeating within each interval of 180 degrees. So between 90 and 170, you also have another line from going all the way to positive infinity, and it's going all the way to the negative infinity. It's not limited. Okay, so those are the curves. So now maybe what's important is you need to remember this first one, which lies between negative 90 and 90. Once you draw this other one, everything else is spaced out use a distance of 180 degrees. So from 90, you put another 180, you'll get to 270. The next curve will be in between there. From 270, another distance of 180, and the next curve will be in between those two, and so on. Okay. So this diagram you're familiar with, I think it's it's what helps you to figure out the signs for the trigonometric functions. So it means it is first quadrant from 0 to 90 degrees. All the ratios will be positive. All the ratios, the sine, the cosine, and the tangent will be positive. If we are between 90 and 180, the sine will be positive, all the others will be negative. Tangent and cosine will be negative. Between 90 and 270, the tangent is positive. Is that correct? Tangent is positive. And between 270 and 360, the cosine is positive, and the rest are negative. So we can, it may be useful to look at this from the graphs. If we go back to, here. So this is a graph of the cosine function. You can see from 0 to 90, it is above the x-axis, so it is positive. Between 90 degrees and 270 degrees, it is below the x-axis. That means it's negative. And then it becomes positive again from 270 degrees to 360 degrees. So that's why you can see the cosine is positive here, and also the first and the last quadrant. So you can do the same for the sine function. You go back and look at the graph, and you'll see the same thing. It's the sine of theta. So for the sine, you can see from 0 to 180 degrees, it is above the x-axis. So it's always positive between 0 and 180 degrees. Between 180 to 360, it's below the x-axis, so it's negative. So the graph tells you all this information as well. So I think when I was in school, we used to say all cats take soup. I don't know what you say these days. So how you remember this is all cats take soup. So I didn't list this table, but there are some common angles like 30 degrees, 45, 60, and so on that occur frequently. And it would be useful to know their trigonometric ratios. I did not put the table, but since we will not be using it much later, so it may not be very important for now. There's someone whose microphone is on. Can I think they are quiet now. So there are also some more trigonometric ratios, the reciprocals of the tangent of the tangent, rather sine, cosine, and tangent. And this is what you get. Secant theta is the same as 1 over cosine theta. Cosecant theta is the same as 1 over sine theta. And the cotangent of theta is the same as 1 over the tan of theta. Again, we may not use this so much. Maybe in the next presentation, we will do the graphs of these functions as well. So if you apply the Pythagoras theorem to this unit circle, you have some new identities which you can come up with. The first one is this. You can see this is a right angle triangle. And these are the two sides, the two shorter sides. This cosine theta, that length, and sine theta, those two lengths are the two shorter sides. So if you get the sum of their squares, it should be equal to the hypotenuse. And we know that the hypotenuse is equal to 1 because the radius of this circle is 1. The hypotenuse will always be 1. So this guarantees us that the cos squared theta plus sine squared theta is identically equal to 1 for any value of theta to pick. Now we can create a few more identities as follows. If we divide throughout this identity by cosine squared theta, here we shall have 1. Here we'll have tan squared theta. And here we shall have 1 over cosine squared theta, which is secant squared theta. So that's another identity. Now, if we divide throughout by the sine squared, we get this other identity, the cotangent squared theta. After some rearrangement, this is what you'll get. The cotangent squared theta plus 1 will be identical to the cosecant squared of theta. So these identities are very useful in solving some problems. I think we might use some of them as we go along. I believe we shall have a second presentation on trigonometry where we can cover some more detail. This one was just introductory and avoiding a lot of detail. So we try to apply some of these things to solve this problem. This one says if the cosine of theta is a quarter and theta is an acute angle, find without using tables or calculators the sine of theta and the tan squared of theta. So we'll go to the solution. So we are given some information. We know that the cosine of theta is a quarter and the sine squared. We also know that this identity holds. Sine squared theta plus cos squared theta is equal to 1. So if we make those substitutions and work it out, we find that the sine squared of theta is equal to 15 over 16. But recall that we were told theta is an acute angle. So we just take the positive square root to get the sine of theta. Because the reason for that is the sine of theta is positive for an acute angle. Any angle between 0 and 90 degrees will have a positive sign. Now that we have found sine theta and we already knew cosine of theta, we can find the tangent of theta, which is this. I think the question wanted the tan squared, right? So this is not complete. The square of this should be 15. I think the answer here should be 15. Because the question is asking for the tan squared. So this was incomplete. But you can correct that. I think it's not a very big mistake. So here is another example we can work out. It says using the fact that the sine of 30 degrees is equal to a half, find the sine of these other angles, minus 30, 150, 210, and 330. So what we're going to do with this one is to play around with the unit circle to find the answers to this. But we know that the sine of 30 is equal to half, so we can use that as well. So this diagram is small. I don't know if you can see it. I may have to get out of the slide mode and enlarge this so that you can. Is the diagram better now?
Yes.
It's much better. So if you want to get the sine of 30, we already know it's a half. So remember, if this is a unit circle, so the sine of 30 degrees will simply be the projection of this line onto the y-axis, right? So this point here will be 1/2. So if you want minus 30 degrees, it will go down the same direction and make exactly the same projection, but in an opposite direction. So this sine of minus 30 will be minus a half, right? Okay, so the next one was what? We had to find some more. Let's check. We had 210, we also have 330. So the 210, if you were to measure 210, you'd start from the x-axis here. You'd go all the way. Here you'll have obtained 180 degrees. To get to 210, you need to add 30 more degrees. So there's an extra 30 degrees here, so that this line, these two lines, this is the same line from P all the way to Q3 and passes through the origin. That means also this projection will be negative. The projection of this line for 210 degrees will be down here, so it will be negative a half. The sine of 210 degrees will be negative 1. 150 degrees, you would have to just remove 30 degrees from 180, so that this is the angle. This angle will also be 30. That means if we project it onto the x-axis, the y-axis rather, we will get the sine of 150 degrees. This is 150 degrees. So we need to project this line onto the y-axis to get the sine. Remember, this is a unit circle, so this is possible. So that means the sine of 150 is a half. And for 330, it means it coincides with minus 30 degrees. You can see that, right? So the sine of 330 degrees will just be negative a half. Because if you have to measure 330, you would come all the way up to there. So it will coincide with negative 30. And also then the sine will be negative a half. Okay. So I think we have covered all this, because this is what we were talking about. This is the one for 150 degrees. This line OQ2 will be the one that makes 150 degrees with the positive x-axis. And the projection is a half, exactly as for 30. The remaining ones are also here for 210 and 330 as well. So that should cover that example. So another way to do this is to simply draw the graph of sine theta and find the intersection of that graph with these two lines. Y is equal to a half and y is equal to negative a half. Again, I have not drawn this, but it's something you can do. So here is another equation which asks us to find the values of theta between 0 degrees and 360, for which the sine is equal to 0.37. Okay, I hope you have read the question. So basically you need to solve this for values of theta between 0 and 360 degrees. So it's possible to use a calculator. Oh, there's a diagram missing here. So the first answer you can get is approximately 21.7 degrees using the calculator. Now, another possible solution within the same range is 180 minus this 21. And that gives us 158.3 degrees. So in the given range, these are the only two solutions. Unfortunately, for some reason, the diagram is not appearing. For this one, it is. For the other one, I don't know why. Maybe I forgot to load it. So the diagram would show you quite clearly what is happening. But you can also, if you recall, there's a relationship we had earlier that says the sine of theta is the same as the sine of 180 minus theta. So that gives you the two values that in that range. If you try to use any of the other formulas, for instance, if you want to add 360 degrees to any of these, you will get values that are out of the range. So these are the only two that are in the range. The other values that work, but the ones that are in the range that we need, those are the only ones. We use the same ideas for this one. So we find the values of theta between 0 and 360, for which the cosine is negative 0.61. Here we use a trick again. Of course, you can do it to the calculator without any tricks, but anyway, you see, what we are looking for is we need the cosine to be negative 0.61, but we start with 0.61 to get 52.4. Once you set up 52.4 here, we can find out all the other angles in that range whose cosine will be negative. Now, the cosine is measured as a projection onto the x-axis. So one of the angles that will give you a projection onto the negative axis is 180 minus 52.4, which is what we have up here. And the other one is 180 plus 52.4, which is what we have down here. You could do the same by drawing the line of negative 0.61 and intersecting with the graph of y is equal to cosine of theta. You'd still get the same point, 127.6 and 232.4 as your answers. So those are the only answers in the range that we need. Here is also another example for the tangent. Find the values between 0 and 360 such that the tan of theta is 2.72. So what we did here is simply drew a line. You can use a calculator, of course, or the tables to find your first value. In this case, we have 69.8 as our first value. And remember, the tangent repeats after every 180 degrees. So we can just add another 180 degrees to 69 to get another value which gives us the same tangent. And the farthest we can get to is 249.8. If you add any more here, you go outside the range of 0 to 360. So the only two values that work in that range are these ones. So this one says find all the solutions of sine theta is equal to sine alpha, where alpha is a constant. And we want alpha to be acute. So now alpha is a number, it's fixed. Okay, just hold on. So alpha is a fixed number. So if you get the graph of y is equal to sine alpha, it will be this constant thing, this dotted line, constant one. And then the graph of y is equal to sine theta is here. So you need to find all values of theta such that sine theta is equal to the sine of alpha. So you just need to find the values of theta where these intersect, right? The first two will be alpha and 180 minus alpha. But then since this curve repeats itself every 360 degrees, then we keep adding multiples of 360 to alpha. We can also add multiples of 360 to 180. If you spend a little time and look at this, you can actually combine both of these into one equation, so that you get theta is equal to 180n plus negative 1 raised to n alpha. So you'll notice that this will be different when n is even, and also different when n is odd. I don't know if, so instead of working them out separately, so for instance, when n is even, you will have multiples of 360, right? So this is a term that you'll be looking for. When n is odd, this is the one you will be, these are the terms you'll be computing, because they're the ones that will have a negative alpha. So when n is odd, that negative is obtained through this value here. But when n is even, negative 1 raised to an even number is still positive. So now this one gives you one consolidated answer. And if you want to compute any value that works, there are infinite number of them. So for any value of n, this will be true. But most of the time when you are answering questions, you will be restricted to a certain interval. But this is just to show you how you can find a general formula for such a problem. We can apply the formula here. Find all the values of x in the range 0 to 360, for which cosine of x plus 15 is equal to sine of 2x minus 15. Earlier on, I don't know if we wrote this down, but we know that there's a relationship between the sine and the cosine, which says that the cosine of theta is the same as sine of 90 minus theta. So that's what we've applied in this. Cos x plus 15 is the same as sine of 90 minus x minus 15. And then we equate it to sine 2x plus 15. So what we do, we treat this 2x minus 15 as our alpha. See this alpha here? And we just plug it into this formula. When we work it out, this is what happens. And two cases arise. When n is odd, we can obtain values of x as 180n minus 60 degrees. And if n is even, the values of x will be given as 30 minus 60n. So you can use this to compute values within the range. I think I did not compute them. But you can compute the values within the range that lie between 0 and 360. Here's another interesting one. Given that secant theta plus tan theta is equal to half, find the values of secant theta and tan theta. So if you don't mind, I will move a little faster. I think we may be running a little over time. I'll try to move faster, but if there's something you don't understand, you can always stop me and ask. So here there's, we make use of this identity. We saw this identity earlier, which says that the secant squared of theta is equal to 1 plus the tan squared of theta, or you can write it as secant squared theta minus tan squared theta is identically equal to 1. Now you can multiply this out as a difference of two squares. Think of it as a difference of two squares, then you factor it out like this, which would be equal to 1. Now we know that this secant theta plus tan theta is equal to a half, so I can just substitute this by a half, right? And when I do that, my equation simplifies to this. Secant theta minus tan theta is equal to 2. So I have two simultaneous equations to solve. The secant theta plus minus tan theta is equal to 2, and secant theta plus tan theta is equal to a half. So those two, when solved, I'm able to find my value of the secant and my value of the tangent. So the secant is 5 over 4, and the tangent is negative 3 over 4. So generally, there may be more than one way of solving these problems. So if you rewrite the equation as just multiply throughout by 2 and write it as this. You can square both sides and solve, and you should still be able to get the answer. The problem is with when you square and solve, sometimes you introduce new angles, or rather you introduce new values which may not work for your original equation. So if you square and solve, make sure that you double check all the values that you obtain and see if indeed they work for you. I think the next example will illustrate this. This one says solve the equation the secant of theta is equal to 3 tan theta minus 1 for values between 0 and 2 pi. So in this case, there's a problem. Part of this problem is cut out. So anyway, we here we do that. We square both sides and use the fact that the secant squared of theta is the same as 1 plus tan squared of theta. When we make that substitution, we simplify everything to this now. 2 tan theta plus 4 tan theta minus 3 is equal to 0. So this gives us two options, either that the tan of theta is 0 or the tan of theta is 3 over 4. Some of it was cut out, but basically you've gotten the idea of how this is worked out, and we are running out of time. So we'll quickly go over this. What happens? Sometimes you're interested in knowing what happens if you, all the graphs you worked before had a coefficient of 1 in front of the function. What happens if you change the coefficient? So we try this with 2 sine theta. And when we do that, we end up with the following situation. So the dotted line is just a graph of y is equal to sine theta. Then the red line is a graph of y is equal to 2 sine theta. You can see that everything in sine theta is multiplied by 2. So what changes is the maximum value moves to positive 2, and the minimum value is negative 2 for the graph of sine 2 sine theta. So this graph has a new maximum and a minimum. But they cut the x-axis at the same 0 points. The zeros are the same. Where they cut the x-axis does not change. They all remain the same. The only thing that changes is the magnitude. So this means even the period is the same. They move at the same pace. So the other thing we need to look at is what happens if you multiply the angle by a number. So we do this with the graph of cosine of 3 theta. Again, we compare this. Now the dotted line is a graph of y is equal to cosine of theta. And then the red line is a graph of y is equal to the cosine of 3 theta. So you can see that the graph of cosine of 3 theta seems to be compressed. But the one for cosine theta seems to be stretched out, right? So when you multiply the argument in here by a number like 3, for instance, you compress. What you also notice, the maximum and minimum do not change. They are still 1 and negative 1, but the period definitely changes because now a complete wave is done in how many degrees? Is it 120? Yeah, I think in 120 degrees because it starts from here and completes the wave here. 120 degrees give you a full wave instead of the 360 degrees. So when you multiply by the angle in the argument by a number, you change the scale, the x-axis. So what about if we add a number to the angle? What happens? So we need to sketch the graph of sine of theta plus alpha, where alpha is a positive constant in this case. So that's the example we look at. So when you draw this, you will notice the following. Now the graph of y is equal to sine theta is given. And the one for y is equal to sine theta plus alpha is the red one, this one. And you can see what has happened is that it has moved back alpha units. So it is behind by alpha units. The maximum and minimum do not change. It moves behind, and now even the points at which it cuts the x-axis have changed. They are no longer the same. It has moved back. So based on this, we can make some conclusions, but I think this will be covered in, we will have to do another talk on trigonometry where we can cover this in detail. So in general, if you have all these terms, you multiply by a number, multiply the argument by a number, and add a constant, then you make some changes. You change the maximum value to A and the minimum to negative A. And that is what we call the amplitude of the wave. And the period is 360 degrees divided by this constant K. Or if you want it in radians, it will be 2 pi C K. Like in the previous example, you saw it was 360 divided by 3. That's what gave us 120 as the new period. The new period was 120. And we got that, we can get that by dividing 360 by 3. So, and this alpha is called the first angle. So, I think I'd like to stop there. If there are any questions, we can take questions. I know we are past time. If there are no questions, we can also, you can still hear me?
Yes, Dr.
Yes. Are there any questions? I was a bit pressed for time, so I didn't prepare some sample questions on this topic, but I think I will put them together and we should be able to get them on the KKMO website. Though we shall do another talk on this to cover the waves in more detail and also cover a few other trigonometric identities. Yes, is a question? Also, the video will be available. I will do a recording of the video and it will be available.
Yes, I have a question.
On YouTube. Usually share the link from YouTube. We'll also put it on our Facebook page once it is ready, the video. Our Facebook page is KKMO. Let me see if I can put it in the chat. So our Facebook page will be, just look for KPEC Kenya on Facebook. KPEC Kenya Mathematical Olympiad. Once I process the video, I will post the link there. Someone who is asking about the notes. I'll put my email here. Okay, there's a lot of comments. I'm trying to go through the comments. Yeah. Yeah. Okay. There are many comments I can see, but I may not be able to respond to all of them now. So the we will organize for another class where we can cover more on the trigonometry in detail. And if you have any suggestions on what we can do, please let us know. If you think we should continue with the same topic. There's a lot more that can be done in this topic. So if you would like to cover more, we can do. There's some more interesting stuff on trigonometric identities that we can do. And also do more on the webs, because we only touched on the webs for briefly. There are no more questions, I think. So we can wish everyone a great evening. And thank you all for showing up. It was a very well-attended class. I hope you found it useful.
Yes.
Yes.
So we'll be back again in 2 weeks. Now you may feel free to leave at your leisure and pleasure.